When we look up at the night sky, we see all these points of light. But what's amazing is that some of those points, they aren't single stars. They're entire cities home to hundreds of thousands of them. Today, we're going to dive into one of those cities, the globular cluster Messier 9. But here's the catch. How do you even begin to understand something so massive and so far away? Okay, just take a look at this. This is Messier 9, also known as NGC 6333. It is this incredible, breathtaking ball of ancient stars, all packed together in the constellation Ophiuchus. We're talking about one of the oldest objects in our entire galaxy, and this is what we're going to be exploring today.
And that really gets us to the heart of the problem. This stellar metropolis, it's almost 26,000 light-years from us. That is a number so big it's hard to even imagine. Something like 150 quadrillion miles. So how on earth can astronomers measure its distance, its age, or what it's even made of from that far away? Well, that's the exact puzzle a scientific paper from 2013 set out to solve.
To even start, you really have to wrap your head around the scale we're dealing with. Messier 9 is basically a relic from the early days of the universe. It's this dense swarm of stars that have been orbiting each other for billions and billions of years. But just looking at the whole thing at once, it doesn't give us the answers we need.
So here's the key idea. The secret to understanding this entire city isn't in its skyline, it's in its citizens. The astronomers behind this study, they knew they had to shift their focus, go from the huge, big picture down to the tiny details held by a few very special, individual stars inside that cluster.
So, what makes a star special in this case? Well, it's all about the flicker. The clues that unlock everything we want to know about Messier 9 come from a certain kind of star. One that doesn't just shine with a steady, constant light. They're called variable stars, and this paper zooms in on a very specific type known as RR Lyrae stars. Now, think of these stars as perfectly calibrated cosmic lighthouses. They pulse with a rhythm that is directly and super reliably tied to their intrinsic brightness, that is, how bright they actually are up close.
And that's the beautiful trick, right? If you know how bright a light bulb truly is, say it's a 100-watt bulb, and you see how dim it looks from way down the street, you can calculate exactly how far away it is. These RR Lyrae stars give astronomers that known wattage. It's this wonderfully simple concept that lets us measure the absolute vastness of space.
But, knowing the method is one thing. Actually doing it is a whole different ballgame. The team faced two massive challenges trying to decode that faint, flickering starlight coming from the heart of Messier 9.
First, just the crowding. The core of a globular cluster is one of the most densely packed places in the entire universe. Trying to pick out one faint, flickering star from that chaotic storm of light, it's like trying to hear a single person whispering in the middle of a roaring stadium. It's almost impossible.
So to solve this, they use this incredibly clever technique called difference image analysis. Here's the gist of how it works. You take a perfect, crystal clear reference photo of the cluster where everything's stable. Then you digitally subtract that reference image from every new photo you take. All the constant stars just poof, they disappear. The only thing left behind is what has changed, the flicker of the variable stars. It's a genius way to silence the crowd.
The second big challenge is cosmic dust. Yeah, just like smoke in the air makes a sunset look redder, the dust floating between us and Messier 9 scatters blue light. This makes the stars look redder and dimmer than they really are. This reddening effect can throw all your calculations way off, so the team had to use these detailed maps of interstellar dust to correct for it, very precisely.
Okay, so after jumping through all those hoops and overcoming these hurdles, what did the team actually find? Well, they managed to pull back the curtain on Messier 9, and the payoff was absolutely huge.
First off, they found new citizens in this city of stars. Their super precise method allowed them to identify 13 new variable stars that nobody had ever seen before, all hidden away in that dense core.
Next up, the distance. Using those RR Lyrae standard candles, they pinned the distance down to about 8 kiloparsecs. Now, a parsec is a unit astronomers use for just ridiculously huge distances, and 8 kiloparsecs translates to roughly 26,000 light-years. This confirmed older estimates, but with incredible new precision.
They also measured the cluster's metallicity. Now, in astronomy, metals is kind of shorthand for any element heavier than hydrogen and helium. A value of -1.70 means that Messier 9 has only about 2% of the heavy elements that our Sun has. And that's a chemical signature that tells you this thing is
ancient, confirming it formed in the very early, less enriched universe.
But the discoveries didn't stop with the big picture stuff. Their high-quality data led to this fascinating little cosmic detective story, and it all revolves around a star named V12. For the longest time, it was classified as one type of variable star, a population 2 Cepheid. But the new, more accurate data, it just didn't fit.
The paper points out that V12 was simply too bright for its pulsation period. As this quote explains, it perfectly matched the profile of a different and much rarer class of star, an anomalous Cepheid. They literally had to rewrite the identity of this star because they had better evidence. And that's a perfect lead-in to our final section.
Because, you see, the story of Messier 9 isn't just about discovery, it's also about refinement. It really highlights one of the most important but maybe overlooked parts of the scientific process, being willing to take a second look at your own work.
So what happens when you find an error, not in some old data from decades ago, but in your own brand new analysis? Do you try to hide it? Absolutely not. If you're doing science right, you announce it to the world.
And that is exactly what happened here. 3 years after their big paper, the same authors published an Erratum, which is basically a formal correction. They'd found that one of the equations they used, one that calculated how the pulsation period of some stars changes over time, well, it had a bug in it.
And you can see the direct impact of that bug right here. For this star called V14, the original paper calculated its period was changing at a rate of about 4.7 days every million years. But with the corrected formula, that value almost doubled to about 9.2 days per million years. That means its pulsation cycle is actually getting longer, even faster than they first thought.
And this is the most important part of this whole story. This was not a failure. It was a success. The whole goal of science isn't to be right the first time, every time. It's to get closer and closer to the truth. By finding and publishing this correction, the team made their own groundbreaking work even more reliable and even more valuable for everyone who came after them.
So what are the big takeaways here? Well, we've seen that the tiny, faint pulse of a single star can literally be a yardstick to measure the entire cosmos. We've learned how these ingenious digital techniques can uncover secrets buried in a blizzard of starlight, and, maybe most importantly, we've seen that science at its best is this living, breathing process of discovery and, just as critically, self-correction.
And it really leaves you with a final thought. The entire story of Messier 9 was written in the faint, rhythmic light of its most unassuming stars. It just makes you wonder, as our tools get even more precise, what other monumental cosmic secrets are out there, hiding in plain sight, just waiting for us to find the right way to listen.